So where does the catalyst show up in this mechanism? Where do we see it?
IO negative.
Okay. I'm going to say IO negative. Why is IO negative the catalyst?
Because it starts in the product and ends in a reactant.
Cool. IO negative starts in the product and ends in the reactant. Is that what a catalyst is? No. That's an intermediate.
Oh, you're right.
Right? So we want the other way around. Your catalyst starts as a reactant and ends as a product. That's your catalyst. You've got to watch out for that and ensure that you're actually getting it in the proper sequencing when you go through a chemical reaction. Okay? There's another question down there, write the rate law for the mechanism, but I actually don't want that right now. So we're going to erase that. What's the rate law for the overall reaction? Talk to the people around you, see what you come up with. Because you should be able to write a rate law. For the overall reaction, I want a rate law. I asked a really challenging question. What's the rate law for the overall reaction? First off, where do you start? Rate, thank you. Start simple. Rate equals your rate constant. Next. Concentration of H2O2. Do we know what order this reaction is? No, the order must be solved from a mechanism, okay, individual steps, or from experimental evidence. Are either of those given right now? No, which means do you know the order? No, it's X. It's unknown. We don't know what it is. Okay, does that make sense? Okay. Given more information, you can start to say what the order is. But until you have that information, that's where you're left. That's still a rate expression. It's just an unsolved rate expression. That's okay. Make sense? Given this mechanism, what's the rate law? So right away, the answer to that would be rate equals rate constant. Now you can slow down. Concentration of O2 to what power? First power. Why? Because when we look at the rate for this reaction, it is dictated based off of the slow step, and the slow step is our first step, which means the rate for the reaction is now going to become rate equals H2O2 to the first power. Are there any other reactants? Yeah? You now have your rate law. Does that make sense? So you're changing the conditions, our rate is going to change, which makes sense, right? Because there's another piece within that. We good with that? Why can we specify the orders for this reaction? Why are we now allowed to specify the orders? Because we know we have mechanistic steps. Those mechanistic steps are critical to us being able to answer this question. If we don't have those mechanistic steps, we can't specify that order unless we have experimental data. Kind of make sense? Questions? Okay, that's not the button I wanted. See if that works. So a catalyst lowers your activation energy, increases the rate constant. If we go through and look at this particular chemical reaction, it is a chemical reaction that we want to do fairly frequently. Okay? If we pushed into your understanding of, and since it didn't step quite properly, 151 chemistry. I don't know why I did it that way, so I'm just going to erase all this content for the moment. Okay. We're starting with C2H4. We add hydrogen and we get C2H6. This is known as a reduction reaction. Reduction reactions are very, very important. If we consider one of our common greenhouse gases that we're trying to get rid of, what is it? Carbon dioxide. Carbon dioxide is fully oxidized. So one of the things we want to do is to reduce it, put hydrogens back onto that structure. That is a challenging reaction to go through and run. It takes tons and tons of energy. This is a similar process, a reduction reaction, right? Different reagents, but similar process. Takes tons of energy and it's very, very slow. So what do we end up doing? We throw in a catalyst. The catalyst in this case happens to be platinum metal, and platinum metal acts as a place that can grab both substrates and allow the substrates to come into the proper contact to go through and produce your products. Your activation energy drops significantly, about halves the activation energy. That's a pretty big drop. Okay? And if we take a look at your rate constant changes significantly as well. Overall reaction rate is about 4 billion times faster. Okay? So that catalyst is insanely powerful as far as this chemical reaction runs. Okay? Kind of neat. It's also very expensive because platinum. Why? Oh, that's why. So enzymes are catalysts for reactions in living things, okay, or cells and organisms. They do effectively the same thing. They bring your substrates together into the proper alignment so that you can get the chemical reaction to happen in a proper orientation. It's that orientation factor that they're really capitalizing on. They can do other things as well, but for the most part, orientation tends to be the biggest driver. So if we're looking at this system, the enzyme has this weird, goofy-looking shape that happens to grab the molecule, put it into the appropriate space, and then water can come through and finish that chemical reaction. Water could have always come through and interacted with, did they actually say what this one is?
Sucrose.
Glucose and fructose. So sucrose, I'm just going to say heterolysis of sucrose into the corresponding sugar compounds or carbohydrates. Okay. Water is present everywhere. Water could run this chemical reaction in and of itself, just random bouncing. But the random bouncing doesn't get the proper orientation. The enzyme helps to ensure that proper orientation so that we can get the chemical reaction to happen at an increased rate. Okay. That weird purple structure that we're looking at isn't necessarily this one, but if we expand beyond the kind of cutesy cartoon into a more colorful, less cutesy, but still cartoon image, what we're looking at is a protein. Proteins are a sequence of amino acids. Those sequences of amino acids, depending on their order, will change shape and orientation so that they will fold to create pockets where your substrate can come in and interact. Right? And that's what's being shown in the big multicolor thing over here. Okay? It's in reference to a particular enzyme. And all those coils and helices are due to the sequence of amino acids within it. Okay? That structure, as complex and nasty as it looks, helps to grab a hold of different substrates, okay, or particular substrate, and catalyze that chemical reaction. And that's pretty wicked. If we go through and look at the left is actually a video that goes through kind of an animation behind it. For the sake of time, I'm going to argue we don't get to watch that today. Okay? However, since you have access to the slides, you can watch it on your own time. I believe it's about a 5-minute video. Play it at double speed. Okay? It walks through the same content that we've already talked through. It just shows it with pictures, moving pictures, as we go through and have those same conversations. We can go through and look at yet another representation of this. Here you're seeing this weird kind of gray-white cartoon image. It's the same thing, right? It's just a different way to represent the protein. And in particular, that blue spot is where your molecules need to interact. Okay? Your substrate needs to come in and interact. And if we go through and compare the top structure and the bottom structure, do you notice anything different about it? What's that? It looks like it closes, yeah. So as the protein binds the substrate, it actually wraps up around it in this particular case. Okay? That motion could do a couple things. One, it could help physically break or make bonds. Right? It could also exclude other reactants from potentially getting in there or things that could disrupt the reaction. Right? It could also be bringing parts of the protein, parts of the protein around so that the chemical reaction can actually occur the way it needs to. Right? The video on the previous slide goes through and talks through a lot of the chemical reactions that are happening in that particular example. Right? Those chemical reactions all involve the protein facilitating the transfer of hydrogen ions back and forth across the molecule. As we transfer those hydrogen ions, it changes the chemistry of the molecule, which facilitates bond breaking or bond making, which is kind of wicked. Okay? If we take a look at the rate of an enzyme catalyzed reaction, why do you think the graph looks like this? It's another blue box, so spend a hot second and talk to the people at your table. Fair play. I very crudely drew 3 graphs on the left-hand side. What are those 3 graphs representing?
Orders.
The orders for your chemical reaction. That top one would be a 0 order, right? Okay. The bottom one would be first order, right? The bottom one would be first order? No, thank you. Yeah, there we go. No, the bottom one's not first order. It's second order. The middle one would be first order. Cool. I know it's 8:30, but let's see how we move. If we go through and consider each of those, if we take a look at the plot that we're looking at for the enzyme reaction, it isn't any one of those. Okay, so what's going on? What does it look like kind of initially? It looks kind of like a first order reaction at first. Okay, it's a little bit off, but we've got roughly a first order reaction. Then what does it turn into?
0.
A 0 order reaction. Why? What should happen to the speed of the reaction as you add more reactant? It should increase. So why does it not?
So after a certain point, so the catalyst obviously is speeding up the reaction. But after a certain point, based on the amount of catalyst that you added, it can only pull in so much relative to the amount of catalyst. So therefore, it becomes saturated, and after
There
a
it
period
is.
of time, the reaction levels off because it's only pulling in and releasing as much as it can.
When we look at that first order reaction, we've got lots of catalyst. Okay? So your catalyst concentration outweighs your reactant concentration. Why does it become 0 order? Well, it's becoming 0 order not because the catalyst is falling apart or dying. It's falling apart because the concentration of catalyst is now less than the concentration of reactant. We've overwhelmed the ability of the catalyst to actually turn over more product. Okay? That's all that's happening. Okay? And it is, I would argue, potentially possible that it's not a first order and a 0 order. It's actually a first order and another first order reaction. But the rate of that other first order reaction is so incredibly slow in comparison to the rate of the first order catalyzed that it looks 0 order. Kind of makes sense? So what we're seeing is that we've overwhelmed the catalyst, and that's what shuts the whole process down. Kind of makes sense? Cool. And since our quiz is on Wednesday, this is all easy stuff, right?
Yeah.
Some people are saying yeah. Okay. If you're not saying yeah, that's okay. You still got a little bit of time, but we should be talking. You should be talking with me a little bit. All right. At this point, what we're going to shift to is kind of specifics or a specific example outside of enzymatic processes into nuclear reactions. Okay. Most chemical reactions involve the transfer of electrons. This is why in 151 it's so critical for you to have learned Lewis structure, because Lewis structure was how we build a molecule with valence electrons. And that becomes important when you try and bring one molecule near another molecule. It's the transfer of electrons, okay, or the exchanging of how those electrons are being shared. Nuclear reactions change this image drastically because nuclear reactions only involve the nucleus. And what's in the nucleus? Only our protons and neutrons. And so what's changing is that we're looking at just a single atom on its own, and in particular, the nucleus on its own, deciding to react or not react. And that react is ultimately it doing something to produce products. So the nucleus has to somehow change to produce those products. These typically involve the release of very large amounts of energy, okay? And it can be slow or fast depending on your individual elements. Okay? If we go back and talk about our 151 with our isotopes, we had different isotopes. In this case, we're looking at lithium-6 and lithium-7. Okay? How do we know we're looking at lithium-6 and lithium-7? The amount of neutrons means I'm looking at lithium or I'm looking at beryllium or boron or carbon.
Well, so the amount of protons would be the same.
There we go.
I don't think it is.
The amount of protons are what's signifying that we're looking at lithium. Whether it's lithium-6 or lithium-7 has to do with the amount of neutrons. Right? And way to take the hard answer, one option was it says lithium-6 and lithium-7, right? Focus on the information you have at hand. Okay? We don't care necessarily about the amount of electrons. Really, we just care about the nuclear state. Okay? Which is why back when you learned atomic structure, you learned atomic notation, okay? Or what Dr. Schneblin refers to as the isotope symbol. Okay? Some textbooks refer to it as atomic notation. I refer to it as nuclear notation, and Dr. Schneblin's referring to it as the isotope symbol. So what is the isotope symbol for lithium-7? Same deal, group talk. See if you can remember from 151 what our isotope symbol would be. Write the isotope symbol for lithium-7. This is a bit of a review, so it could be hard to remember. What does it mean to be an isotope? Right? So one piece of information that was floated out there was we need to know the mass number. So 7, mass number. Is that the only information I need to know for my isotope? You need to know, okay, so there was reference, we need to know 3, the atomic number. Okay, so let's take a look at the word right here, lithium-7. Do you see a 3? Do you need to know the atomic number? You're not entirely wrong, but do you need to know it? When I say lithium, do I know the atomic number? You're like, yeah, if I have a periodic table. You all are chemists. You have a periodic table, period. Welcome to the club. Okay? So do we need the atomic number? No, it could be kind of redundant. But we do need to know either the atomic number or the atomic number is your number of protons. What element are you looking at? Okay, that's kind of important. If I went through and said mass number 7, but then said it was nitrogen, would you believe me? It's a tough, challenging question. Okay, someone said yes, so let's push on that. Let's say oxygen. Oxygen with a mass number of 7. Do you believe me? Ooh, answer changed. Why change?
Because I remember it's 6. It's like 16.
No.
Oxygen would just normally be with having an atomic number of 8, you know, like
8
8 protons.
protons. And why is it a problem for me to say oxygen with a mass number of 7? Yes, it has 8 protons. Why is that a problem?
Mass is protons and neutrons together.
Mass number is protons and neutrons. If I know oxygen has 8 protons, how many neutrons does it have to have a 7 mass number? A -1. That doesn't make physical sense. Okay? So awesome. It's all based off of that mass number. We don't want to worry about the atomic mass necessarily. Okay? At least with the oxygen. Let's drop back to the nitrogen. How about nitrogen with a mass number of 7? No is still a perfectly acceptable answer. But not because, well, it typically has a 14. No, it doesn't. That's the average atomic mass. That's average. We're not talking about average. I'm looking at a case. Can this case exist? Would I expect ever to find a nitrogen with a mass number of 7? So what's the follow-up? We already said no. Why?
That would mean that all of the neutrons have been stripped from it.
It has no neutrons. Why is that a problem?
Because it's has no charge.
No. Charge is irrelevant because what determines charge? Protons versus electrons. And we're ignoring the electrons because the electrons are not in the nucleus. What is the point of a neutron? What?
Is it stabilize the atom?
How does it and it doesn't stabilize the atom, it stabilizes the nucleus. What is the mass for hydrogen? Atomic mass. 1, right? How many protons does hydrogen have? 1. So dang, it matches perfectly. What other element matches the atomic number to the atomic mass? Okay, this is kind of cool because everybody's looking at the periodic table scanning, and that's good. But you're going to scan through every single one of those, and what are you going to discover? None of them match. How is hydrogen different than every other element? Helium's a gas, and helium right away doubles.
It only has one proton, so therefore there's nothing that it's in a sense repelling against or being balanced.
What do protons do when you bring them near each other? They repel, like charges repel. This is why electrons, you can only fit 2 in an orbital because they have opposite spins. You can't fit more than 2 in an orbital. Okay? You can't put 2 protons together, otherwise they repel. But if that's the case, how do we get more elements? What are the neutrons doing? Effectively gluing the protons together. So does it make sense to have nitrogen with a mass number of 7? No, because that's putting 7 protons all together. And what are they instantly going to do? Repel away. You need neutrons there to act as the glue. Kind of, sort of? Cool. So mass number we need to know, 7. What else do we need to know? Not the atomic number necessarily, because if I'm saying the mass number, there's certain elements it can't be. What element do I want to look at? It's on the board. On the board. Lithium. I want to look at the element of lithium. Okay. Who wants to know nuclear notation? And I know all of you are like, I don't care about that's not what I'm asking. Who in general out in the world do you think would care about nuclear notation? I don't care about nuclear notation. And we already established you're a chemist, so that doesn't count.
You're talking about chemists or just people in general?
What specific people in general would care about nuclear notation? A nuclear chemist would care about it. Why would a nuclear chemist care about it? Because what do they want to do? When you think nuclear, what do you think? Bombs. So what does a nuclear chemist want to do? Look at the label and be like, whoop, I'm leaving. Okay? So they want to, as quickly as possible, identify that is dangerous. So what's the first thing they want to see? What determines the stability of the nucleus? The mass number. So if we're looking at a notation, since we read left to right, top to bottom, where should we put the mass number? Top left. The mass number is not super important if I don't know the element, so the next thing I want to see is the element. And because we spent time memorizing the symbols, we won't go through and write out lithium. We spent time memorizing that the symbol was Li. Cool. And now if I want to get extra fancy redundant, which is cool, I want to bring in the atomic number, and I'll place that the lower left. Why would I do that? Well, how many neutrons does this have? 7 minus 3 is, it's almost like they wrote it in a math expression so that you could potentially solve for the number of neutrons pretty quickly. Genuinely don't know if that's true. But it looks like it, doesn't it? You laugh like it's, come on, it looks cool. Make sense? This is now our nuclear notation or our isotope symbol. Okay? Make sense? Some isotopes are unstable or radioactive. So this goes back to being able to look at that mass number. We want to see that mass number and be like, oh, that's dangerous. And they know that's dangerous based off of the ratio, okay, of our mass number to our protons or our atomic mass. And it turns out that if we go through and plot, okay, so what this pattern, what this diagram is showing is a little bit hard to tell, but if you look in real close, you'll see little boxes. Okay? What those little boxes are actually referencing is this entire thing is a grid. Okay? The whole thing gridded all the way out. And so if we went through and looked at number of protons 50, what are the odds of having something with 50 protons and 0 neutrons? It's unknown because we haven't found it. And some would argue, kind of like me, that we will never find it. Because what's going to happen? It's going to instantly explode apart. There's no reason for it to exist. There's nothing to hold those protons together. So as we move up, we're slowly increasing the number of neutrons. And then we encounter this first block at, it looks like 49. Okay? And so we're saying 50 protons, 49 neutrons. Did I read the graph right? Yep. And it's colored orange. Why is it colored orange? It's colored orange because it undergoes some type of decay, some kind of radioactivity decay. Okay? As we continue upwards, we'll note that it turns black and then it turns blue. What is black? Black is a stable nuclei. That word. Okay? And what we're saying is that for that particular element with 50, why can't I see it? Tin, there are multiple isotopes. That's why the black line continued to go up. Okay? Multiple isotopes, so different amounts of neutrons that create a stable nucleus. As we continue to go up, the color changes again. The color changes again because now we've added so much glue that the glue starts to fall apart. Okay? Our nucleus starts to fall apart, and we encounter a new form of radioactive decay. And the reason this graph becomes so important or interesting is the black line, if we look at it, roughly equates to a 1-to-1 ratio. For every 1 proton, you have 1 neutron. And we say roughly because initially we only studied the bottom section. And we're like, oh yeah, it looks great down there. It's 1-to-1 all the way through. But as we continue to build and find larger and larger elements, we know it starts to veer off a little bit. Okay? Who would like to study that? Probably nuclear chemists as they're dealing with this. Okay? So they're looking at the stability of the nucleus and how many protons and neutrons. And if we push on that a lot, really what you're going to discover is, you remember how electrons exist in different energy levels and all that? Guess what protons do? The same thing. Okay, do you want to learn about that? Some people are like, yeah, take a different class that studies that. We're not going to talk about that. All we really care about is that it's roughly this 1-to-1, okay, and we need to be aware of those potential processes. Kind of, sort of? That should be a yay moment. You don't have to study it. No? Okay. Yay, thank you. I appreciate it. Okay? So anytime we vary off that black line, we're going to change something about its radioactivity, and the nucleus is going to want to do something to veer back to the black line. The way it's going to do that is those varying states of decay. They've listed out a whole bunch of these states of decay. You've got beta positive, beta negative, alpha, fission, proton, neutron. Okay? What are those all talking about? They're different forms of nuclear radiation. Okay? So there's two major ones that we'll kind of talk about here. You get the alpha decay and beta decay. So let's take a look at alpha decay first. So let's get rid of the beta for the moment. What do you think the rate would be? Sorry, the rate law.
Rate equals K.
And numbers, right? Why are you saying first order? And by why, you don't get to answer.
Okay.
Why did she say first order?
Because
It's a hard question. Go for it. You got it.
I was just gonna say because if we only see one of the elements in the reactants.
So we're talking about the coefficient in front being 1. How many times can you bring the coefficient into your rate law? When are you allowed to do that?
There's no steps.
It doesn't say the word.
Close, but drop a word from that. Okay, what you're referencing is when it is a mechanistic step. That is when you can drop the coefficient down. Have we said that this is a mechanistic step? No. Should it be a mechanistic step? Go for it.
Yes, it's an elemental reaction. I can see one element.
Just because I have one element in a chemical reaction doesn't mean the mechanism is just going to involve that one thing. How carefully are you choosing your words?
Since it's a decay, it's like one atom releases, like, is just releasing.
You might be choosing your words carefully. Okay? If we said one molecule, we don't know that one molecule is necessarily going to produce this way. Since we're showing one atom, there is only one option here. Okay? If we push on this even further, what's happening? What changed? Did we transfer electrons?
No, we dropped two protons.
We dropped protons and neutrons. From what?
It's
From the nucleus. So the nucleus just went. That was a fancy description. Right? It just did it on its own. Therefore, first order reaction. So that's pulling in our understanding of what's happening with nuclear decays that allow us to predict that it's going to be a first order reaction. What did it produce? Okay. TH is a fair statement. Okay. Thorium, do better. What else did it produce? Alpha particle. Okay, the alpha particle is the one I wanted to look at. Do better than alpha. Not you, though. Two protons. You're doing the right thing. Stop it. Two protons, two neutrons. I said do better than alpha. So you broke down two protons, two neutrons. That's lovely. Okay? But I didn't ask that. I said I want better than alpha. What is alpha? Say again?
Helium.
It's a helium. Okay? Because we're taking two protons plus two neutrons. How do we know we have two protons?
says it.
Because in the lower left-hand corner, we have the atomic number. So we can pull that atomic number, use that straight off the periodic table, and say that that atomic number means we're looking at helium. Okay? 4 is the atomic mass. Sorry. Mass number, which is our protons plus our neutrons. So what we're looking at is the isotope of helium-4. Are we emitting a helium atom? Wicked hard question. Be real careful with this. Said another way, when we look at this notation, is writing this equally good as writing 4,2 alpha? That's a challenging question. When we bring in the element symbol, and we go all the way back to our notation, this was our mass number up here. This was our atomic number. What's in the lower right-hand corner? And don't feel bad, everybody trips on this. What's written in the lower right-hand corner of an element symbol? What's that? Nope. Okay, let me give you a good example here, because you've seen it before. You've seen it all the time. What is that compound? In the big circle that I showed. Water. What the heck is that number? What is that 2? It's the amount of hydrogen. Guess what shows up in the right-hand corner? It's the amount of that element showing up wherever you're using it. Okay? When we go through and write a chemical formula, typically we don't care about the mass number or the atomic number. The atomic number was redundant. The mass number we don't care about because the mass number doesn't change with most chemical reactions. So we drop both of those pieces of information off of our chemical formulas. The amount of the times that it shows up is kind of important when we run a chemical reaction. So that's usually specified. This is the amount. What's written in the upper right-hand corner? There it is. Upper right-hand corner is typically our charge. So if we write the notation 4,2 helium, what are we saying? How many electrons does it have? To balance the protons, which means when I write 4,2 helium, I'm saying it has 2 electrons. We're writing it as alpha because it's not that we don't know. It's that it doesn't have electrons. The alpha particle is only the helium nucleus. Okay? It's not emitting any electrons with it. It's just the helium nucleus. Okay? So you might see reference to this notation. It's a bit sketchy because this notation starts to imply presence of electrons, and there's no electron transferred in this system, which is why the alpha symbol makes a whole lot more sense and allows us to manipulate that a little bit better. Kind of good? Right? Why do we have the element thorium? Why did it change identity from uranium to thorium? The alpha particle was a helium nucleus. We lost 2 protons, which means uranium minus 2 protons would be thorium. And we could use our periodic table to predict us out of that. Okay, if we wanted to do it as a number line, we start at uranium with 92, we subtract 2, 91, 90, there it is, thorium. There's our system right out of it. Kind of, sort of? Cool. There's other kind of decays. Okay, there's a beta decay. What's going on with the beta decay? What do we write in the lower left-hand corner? We write our atomic mass, which would be our number of protons. And here we have a negative. This doesn't really make any sense. Okay? What's happening here is you're ejecting from the nucleus an electron. And when you eject that electron from the nucleus, what happens to your nucleus? I'll come back to you in a second.
Did you say inject or eject?
Eject. Lost. What would happen to your atomic number? Well, if I lost an electron, why would that change my atomic number at all? How many electrons are in the nucleus? 0. So how did I lose an electron? Look at your atomic number. What changed? Effectively gained a proton. So what happened is we rearranged that matter, and in the process of rearranging that matter, we lose that electron, or lose the negative charge, which is going to produce a new positive charge. Isn't that wicked? I think that's wicked. Okay? And so that's what that atomic number is referencing. Okay? Can we reference it as just an electron? No, because there aren't really electrons there, which is why we're talking about it as a beta particle. Okay? All we're dealing with is looking at those masses and how those things go through and change. Kind of, sort of? Just happened to dawn on me. Where did the extra proton come from? Came from, it's exactly what I thought. Oh, it came from a neutron. But if we change our number of neutrons, it should have changed the mass too, right? Okay, a little bit questionable because you're changing the neutron, and instead of being a neutron, you're making it a proton, which means your mass actually probably won't change in that respect. What else is changing here? A wicked amount of energy. And you're like, well, but energy's not matter. But isn't it? What's Einstein's equation? E for energy equals m for mass. They are directly related to each other. And if we're exchanging the energy, we can actually deal with exchanges of mass. That's kind of crazy. Okay. Ignore that. There was a slide a little bit later on that I missed, right, or that was added and I should have shuffled around. You could also look at something known as positron emission. Okay, positron emission. Now we're ejecting something with a positive. Okay, so because it's ejecting with a positive, we expect to see our atomic number go down. Because, oh, we're losing a proton. We might say, yeah, we're losing a proton. That makes sense because our atomic number went down. Except what's the mass of a proton? 1, which means what should happen to my mass number? It should go down, and yet, it stays the same. So it's not the loss of a proton. Okay? It's the loss of a positively charged particle that has no mass. And if we call negatively charged particles electrons, what should we call positively charged particles with no mass? Positrons. And there's the existence of that new system. Kind of, sort of? Okay, and because you've had all of 10 seconds to practice it, have fun. So we'll walk through this hopefully kind of quickly. Right, the atomic number is something we need to find, which means we do need to find the element on our periodic table, which as walking around I equally struggled with. So for plutonium we got 94, lead we've got 82, and for oxygen we have 16. What's wrong with 16? What's wrong with 16? That's the mass. What is it supposed to be? Not 9 either. 8, because it's our atomic number. Okay. Okay? If we're looking at the alpha particle, okay, what's going to happen? We're going to lose 4. So 239 minus 4 would be 235. We're also losing 2 protons, which means 94 needs to become 92. Now that we know our atomic number, now we could backtrack what that is. Uranium. For the next one, what do we go through and do? Same deal. Our mass number is not, well, not same deal, but same process. Our mass number is not changing. So we got 214. What's happening to our atomic number? Needs to go up by 1. Now that we know our atomic number, we can look it up. What'd you say?
Yeah.
I looked at 93. Sorry. BI. Our mass number does not change, so we're at 15. Okay. Our atomic number does change, which means we'll drop to that 7, and we're getting nitrogen. Make sense? Questions about that?
So, if plutonium decays and then becomes uranium, an alpha particle, theoretically, couldn't you do that and actually change lead to gold?
So there's a good question. If we're talking about our radioactivity and how these things kind of transition, okay? So, and in particular, what he was asking was not where I thought he was going to go. So we'll go where I thought you were going to go first. Okay? Plutonium is reactive. Is uranium typically nuclear reactive? Yeah. So what is uranium now going to do? It's also going to decay. So typically when we talk about these radioactive byproducts or the products of these reactions, they're going to produce more radioactive products. And the reaction will continue to cycle until what? They reach the line. They reach that stable line. Okay? But what you did bring up here is that theoretically, if you had lead, could lead decompose into gold? Yeah, why not? Okay? Theoretically, yeah, it could go through and do that process. What does it require? That you have radioactive lead, okay? You have a radioactive nuclide of lead, and that lead particle decomposes in such a way that you would produce gold. Okay? And for the sake of your argument, which is probably like, hey, we can turn lead into gold, not just that lead is converted into gold, but that the gold that we produce is also nuclearly stable. Because if it continues to decompose, that's not worth anything. Okay? So could we theoretically do something like that? Theoretically, I'm sure that has been studied in great depth, and you could poke at it and say what kind of particles and radioactivities you would need to do. And what I think you'll end up finding is the amount of lead isotope that is necessary to allow that decomposition pathway is probably less common than raw gold. So not particularly useful.
So is that how they discover new elements? They just throw alpha particles at it?
So when we talk about the discovery of new elements, that brings in a whole nother thing that is way outside my scope, but my understanding is that they are smashing nuclei at each other. Okay? What nuclei are they smashing? Okay? It can be alpha particles trying to smash them in. It can also be 2 large atom nuclei and trying to smash them, okay, into each other. That's, I believe, what they're doing at the Hadron Collider. Right? They're trying to smash those and look for other things. But if they happen to discover new elements at the same time, they're excited about that too. Oops. So our products of nuclear reactions, alpha and beta particles, typically not harmful to humans unless you ingest them, okay, or exposed to a lot of them. The larger issue is that our nuclear reactions release a lot of energy. And when that energy hits you, that's a little bit of a different story. Okay, so when we're talking about that energy, we're usually looking at things way up into your gamma and X-ray radiation, and those are such high energy that they will ionize any bonds. Okay? And say if your molecular structure gets ionized, what happens to the bond? It breaks. That's generally not pleasant for the things that keep us alive.
So, like, quick question, kind of related to this. Is it like PET scans and like CT scans in that correlation with like X-rays? Because I know that they.
So CT is for sure X-ray. I don't know enough about PET. They are lower energy on that X-ray scan. But yes, they are dangerous, and they do ionize. Okay, but you're looking at concentration. This is why whenever you get an X-ray, what does the attendant do? They go outside, okay? Because they don't want to be hit by it. You're like, well, I'm getting hit by it. But you're getting hit in a single dose. If their job is today, do that to 30 people, they're getting constantly hit by it. That's now a problem. And even when you're getting X-rayed, they don't just X-ray everything. What do? They put a lead vest over you. The lead vest protects from that radiation. But yes, that is exactly what's going on in that process. So who was the primary discoverer of this? Marie Curie is pretty cool in this respect. She got 2 Nobel Prizes. I think she's one of 2 people now that have 2 Nobel Prizes. The other one is Pauling, I think. But hers are both in science, whereas Pauling's, I think, is chemistry and not science. I don't remember what his other one is, but not science. So she's pretty awesome. She spent a whole lot of time going through trying to actually isolate the radioactive isotopes so that they were discovering that there were certain things that were kind of creating weird emissions, and they processed and purified that to get to larger concentrations, because once it's now pure, you can state something about its identity. And that's pretty wicked. Okay? Fascinating lady. 151, you probably talked about her a little bit more. No, not 151 either. Oh, that's kind of a bummer. Yeah, Rutherford's experiment. Okay, what did Rutherford's experiment do? You're all like, oh, yeah, I know Rutherford. And then I was like, what did he do? No, okay. You could just say no from the beginning.
Projected light through a gold beam and refracted.
Okay, projected something at a gold film, okay, and that something either penetrated or bounced. What was the something? It was alpha particles. Alpha particles as in radiation. As in, where the hell did he get alpha particles? Curie supplied them. Curie actually supplied the radium that allowed for that experiment to exist. That's kind of wicked. Right? You could make the argument that Curie is the one that provided the incentive or the skill set allowing us to understand atomic structure. That's pretty cool. Right? So, fascinating lady. I admit, I think she's probably a little bit scary because she's really smart. And to my understanding was, yeah, pretty phenomenal. I believe her daughter also got a Nobel Prize, which is also kind of neat. So that whole family is just filled with brilliant people. Which takes us to some practice. Determine the rate law and rate constant for the beta decay of krypton-89. In this case, okay, the last time we looked at a rate law, we cheated. We cheated because we said mechanistically it only made sense for it to decompose in and of itself, right? Right? Can't cheat this time. Prove it. Prove it using the data that we have at hand. Okay, so if we're going to try and determine the rate law and the rate constant, for me personally, where I would like to start would be what I think the rate law is going to be. So rate equals K. I would get sloppy and drop the mass number and the atomic number. And then this would be to an unknown order X. That unknown order X, when we last talked about nuclear decays, we said based off mechanism it made sense for it to be 1. Now it's not a question of it makes sense. You have data. Use the data to make that order valid. Okay, so this is going back to using that mechanistic data and trying to process through it. You have 3 sets of data here, or 3 sets of experiments. You can pick any 2 experiments, because what you're trying to do is compare them. Okay? If you go back and look at our slides or our discussions on it, what we're talking about is setting up the expression along these lines, KRX. Oops, I'm going to erase all that. KR for the first one, KR for the second one, to the X power. Whereas for first and second can be any experiment that we want to do. Okay? So some people spent some time to carefully look at this and decide which experiments they want to do. That's fine. You can absolutely do that, but we need some evidence to be written down, some calculations, some work to actually explain what's happening within this. Okay? So, please just be aware that you need to go through and do something like that. Does that make sense? Okay? What work do we need to go through and see? Well, pick some experiments. Okay? Rate 1 and 2. What experiments do you want to compare? 1 and 2, 2 and 3, 3 and 1? 1 and 2. Okay? I'm going to set it up this. I'm going to put 2 on top, so 0.05 over 0.01 equals 1.83 times 10 to the minus 4th over 3.66 times 10 to the minus 5th to the X power. Okay? So I put experiment 2 over experiment 1. Okay? This can be inverted. Doesn't really matter. Why would I pick that system? What is 0.05 over 0.01? 5. What is 0.83 times 10 to the minus 4th divided by 3.66 times 10 to the minus 5? What must x be equal to? X has to equal 1. That supports our evidence all the way through. Does that make sense? You get it? I know I swapped those numbers on you. Okay? That works. Okay? Other people looked at it and they're like, well, I can't believe someone actually pulled this one off, but they did. They were like, well, if I take 1.83 and I double it, I get 3.66. I don't know what the hell you're doing in your head to see that, but good job for that. Okay? You could have looked at the 0.05 and said 0.05 doubled would be 0.1. Like, I'm on board with you there, but what? Good job, I guess. If I'm amazed, you know. Okay? And if that's a doubling for both, what does that mean? The order was 1. Okay? That was something that you could do by inspection. Okay? When it comes to a quiz, you need to be less inspection and more explicit with your work. Make sense? Once you know the order for the reaction, all of that, because I don't have space to include it all, could disappear. Our rate equals K times our krypton to the first order. We then pick any experiment we want, sub in rate, sub in the concentration, solve for our rate constant. Make sense? Okay. With that, I'm going to say we're done. I might try and go through and make a recording of the remaining slides. The remaining slides are mostly informational. Okay? I don't think I will absolutely say I don't think any of them show up on the quiz on Wednesday. But they're informational, provide the context for why you're learning this kind of thing. Kind of make sense? With that, I'm going to stop the recording. If you